Let's all together read this problem. An 8.9 kilonewton car is traveling at an elevation of 1,500 meters with equivalent air density of 1.0567 kilograms per cubic meter on paved surface. If the car is traveling at 110 kilometers per hour and has a drag coefficient of 0.4, and the frontal area of the car is equal to 2.0 square meters, and the available tractive effort is 1,135 newtons. What is the maximum grade that this car could ascend and still maintain the 110 kilometers per hour speed? So in this problem, with all the given information, we are asked to find for the maximum grade, G, capital G. So let's identify what are the given in the problem. So we have the weight, which is equal to 8,900 newtons, the air density, we have the speed in kilometers per hour. Usually we have to use the meters per hour in our calculations. Drag coefficient of 0.4, frontal area of the vehicle, which is equal to 2 square meters, and then the available tractive effort, which is 1,135 newtons. So we're going to find G. Where can we find G? To maintain the speed, the available tractive effort will be exactly equal to the summation of resistance. There is no tractive effort that will remain for the vehicle acceleration. So ma is equal to 0. Therefore, our equation becomes F is equal to the resistance that include the aerodynamic resistance, the rolling resistance, and the grade resistance. It is in this term, Rg, where we can have the grade, the G, which we are looking for. So our formula for Rg from our previous slides is equal to the weight of the vehicle times G. So it's 8,900 newtons times G. So this is our Rg, which we're going to substitute here. Now, let's find RRL, the rolling resistance, and the aerodynamic resistance, and we will equate it with the available tractive effort. So in the next slide, we are solving for RA. And in our previous slides, this is our formula for RA. So we just substitute the information of rho, and then the drag coefficient is 0.4, the frontal area is 2, and then the speed is 100 kilometers per hour. We divide it by 3.6. That is to convert it to meter per second. Okay, so calculating this, we can get RA is equal to 394.63 newtons. Now, we solve for the rolling resistance. We have the formula of F is equal to 0.1 times 1 plus V over 44.73. So substituting the V, we have here, and then we multiply it with the weight of the vehicle, which is 8,900 meters. So if we calculate this, we have the rolling resistance is equal to 149.8 newtons. So therefore, with our first equation in our solution, F is equal to the summation of all the resistance, and we are given the F. It's equal to 1,135 newtons is equal to the sum of, this is the aerodynamic resistance, the rolling resistance, and then this is the grade resistance. And solving this equation, we can therefore solve for G, which is 6.64%. So that solves our example number 1, determining the vehicle tractive effort and considering the resistance forces. The next part of our lecture is on the maximum tractive effort. So what is this? Okay, the maximum tractive effort is the point beyond which additional force merely results in the spinning of the tires and does not overcome resistance or accelerate the vehicle. So it's the tractive effort we're in, even if you try to accelerate this vehicle, it will not be in further motion. So it means that the tires here will just continue to roll and roll without effect on the movement of the vehicle. So there is a point of maximum effort that can be exerted by the vehicle. And the maximum tractive effort is determined by considering the normal forces acting on the front and the rear wheel. Okay, if you look at the forces again, acting on the road, so we have normal forces acting on the wheels. So it should be the efforts that are normal to these wheels. Okay, so let's look closer to this figure. Let's look into detail of this figure again. The normal force that we're talking about, normal to the tires, are these: the WF and the WR, and these are the weight of the vehicle on the front and rear axle respectively, and the distance from one tire to another is what we call the wheelbase L. And then we have the height of the center of the gravity with respect to the road, that is here, H. And let's take note that we have a coefficient of road adhesion, or the friction, that is according to the contact between the road and tire. Okay, and then if this is the center of the gravity, from this point to the front wheel we have LF, and then from the center of the gravity up to the front wheel we have, or rear wheel, sorry, that's LR. So we have this distance from the front or rear axle to the center of the gravity. Okay, so the same thing when we take the summation of forces at this point, then we can have the value of the normal force, the weight of the vehicle at the rear wheel. So we will have the maximum tractive effort at the rear wheel is equal to mu times the weight of the vehicle times the distance from the front wheel minus the product of the friction times the height of the center of the gravity. And then you divide by the wheelbase times 1 minus mu times h over L. Now, if we take summation of forces at this point, then we will derive the formula for WF for the front wheel. So this is it. Okay, take note of the difference of these two equations are this. Okay, the sign here, and this is LR, this is LF, and then the sign here as well. Plus here we have minus. So please take note of this formulas in determining the maximum tractive effort at the rear wheel and the front wheel. So let's have another example, and this is on how to determine the maximum tractive effort. Let's read this problem together. An 11 kilonewton car is designed with a 305 cm wheelbase. The center of gravity is located 55 centimeters above the pavement and 100 cm behind the front axle. If the coefficient of road adhesion is 0.6, what is the maximum tractive effort that can be developed if the car is a front-wheel drive or a rear-wheel drive? So basically what we are asked to find is the Fmax, the front wheel, and Fmax at the rear wheel. So the given information we have here is the weight of the vehicle, the wheelbase, the height from the surface of the road to the center of the gravity, the distance from the center of gravity to the front wheel, and then the coefficient of road adhesion, which is 0.6. Now, to solve this problem, first we solve for the front wheel drive using this equation which we had in the previous slide. Now, first let's solve for F here. We have LR, we can calculate it by wheelbase L minus LF. We have mu, we have W, we have L, and we have this information. So how do we determine F? Using this equation, since the velocity is 0, then when you substitute 0 here, it's 0.01. F becomes 0.01. So we use this value, input it here, and other information. So mu is 0.6, and then the weight is 11,000. And for the LR and the H and the wheelbase, you can either use in centimeters or meters as long as they have the same units. So this LR, the H, and the L, they should have the same unit. So here we use the centimeter values. Okay, so we substitute. This is the LR, this is the F, this is the H, and this is the wheelbase L. And substituting others and calculating it, the maximum tractive effort is more than 4,000 newtons. So that's for the front wheel drive. Next, let's solve for the rear wheel drive. Using this formula that we have seen in the previous slide and substituting the values of the coefficient of adhesion, the weight, the distance from the center of gravity to the front wheel, the F and the H, and other information here, we substitute the values and then we are able to calculate the Fmax for the rear wheel drive is equal to 2,413.13 newtons. So that's how to apply these formulas to determine the maximum tractive effort. The last but not the least that we are going to cover here are the principles of braking, and it will be seen in the next video.